Hello, everyone. This is Richard Bayonta from Lawrence Livermore National Laboratory in sunny California, and I will be speaking about the work my colleagues and I have done on the real-time nuclear activation diagnostic for measuring neutron angular distributions at the National Ignition Facility. And here is my summary. The RT-NAT array at NIF provides advanced capabilities for measuring neutron angular distributions for determining implosion symmetry at NIF. I will show you how, by continuously monitoring the 909 kilovolt gamma from the decay of 89 zirconia, the RT-NAT array measures 14 MeV neutrons along 48 lines of sight with high statistical precision. Finally, I will speak briefly about new work in progress, which includes direct determination of fuel areal densities from the RT-NAT data, measurements of hotspot velocity, and analysis of the signal from DD neutrons. The uniformity of the angular distribution of neutrons emitted by the implosion is directly related to the uniformity of the compressed fuel assembly, and therefore an important diagnostic of implosion performance. We measure the neutron angular distribution at NIF with an array of zirconia nuclear activation detectors, which detect neutrons through the N2N reaction on zirconia 90. The resulting unstable 89 zirconia nucleus has a 3-day half-life and eventually emits a easily detected 909 kilovolt gamma. The important thing about this N2N reaction is that it has a 12 MeV threshold and so is insensitive to the numerous low-energy neutrons which have scattered around so much that they've lost all of their directional information. Furthermore, as the plot shows, the cross-section is linear across the 14 MeV peak, making it insensitive to thermal broadening. The one disadvantage of the linearly rising cross-section is that the resulting activity is sensitive to the center of mass motion of the neutron-emitting hotspot, which Doppler shifts the neutron energy, sliding the peak up and down the cross-section. The hotspot velocity also introduces a smaller focusing effect, which increases and decreases the number of neutrons hitting the detectors. We use the hotspot velocity measurements from neutron time of flight spectrometers to correct for these effects. We currently run 48 real-time nuclear activation diagnostics on NIF, each consisting of a zirconium cup surrounding a lanthanum bromide crystal spectrometer with built-in pulse height analysis electronics. The detectors are permanently mounted on the target chamber and continuously take 10-minute spectra 24 hours a day, 7 days a week. This allows us to keep track of the residual activity from previous shots. The data is stored in a serial database in near real time. Here is a sequence of 10-minute spectra taken over a time span of 39 minutes to 18 days following a high-yield DT shot. The horizontal axis is the MCA channel number with one channel roughly equal to 1 kilovolt of gamma ray energy. The vertical axis is the number of counts per channel on a log scale. At early times, the spectra are dominated by a smooth beta background. Although a few lines are visible, on the left are lines from the decay of short-lived activated bromine isotopes from the bromine in the crystal. Also visible is the 844 kilovolt line from 56 manganese, which has a half-life of 2.5 hours. After a couple of hours, the 909 kilovolt line from 89 zirconia emerges from the background, and this is the line that we use to measure the 14 MeV neutrons. The manganese line is close to this line and complicates the analysis. Also visible is the 511 kilovolt E plus E minus annihilation line and the 1368 kilovolt sodium 24 line from neutron interactions in nearby aluminum. More about the neutron reaction at the end. After a long enough time, the backgrounds are low enough that low-level lines from naturally occurring lanthanum-138 and activated cerium are visible. You may have noticed that the energy scale changes with time. That is, the positions of the peaks change with time. This is not surprising, given the lengths of time involved. Because of this drift, we cannot simply sum over a fixed set of channels to obtain the zirconia counts. but instead must first determine the energy scale for each spectrum, then look in the region corresponding to the 909 line. This is done in 3 levels of processing. The first level simply extracts the raw data from the serial database, assembles it into spectra, and stores them in a relational database, allowing the spectra to be easily accessed for monitoring and software development. The second level identifies the peaks in the spectra and uses them to determine the energy scale and where to extract the zirconia counts, which it then assembles into decay curve. The third level measures the shot-induced jumps in the decay curve and converts these jumps into yields along each line of sight, which we plot as sky maps. To find the peaks, we make use of the fact that the peaks are Gaussian, whose widths are related to the channel number of the centroid. This is because the peak widths are due to fluctuations in the number of primary photoelectrons traversing the first stage of the photomultiplier tube. This gives rise to the so-called photon transfer curve, relating the sigma squared of the peak to the mean channel number. And you can see this linear relationship in a plot of the sigma squareds versus centroid position for a typical RT-NAD detector. Interestingly, if you read about the photon transfer curve, you will find that the gain coefficient gives the number of channels per photoelectron and is seen to be close to 1/10 of a channel per photoelectron for the RT-NAD detectors. In any case, valid peaks, as opposed to fluctuations or broad background features, must lie on this curve. The peak finder attempts to fit Gaussian shapes centered on each of the 2048 channels. That's 2048 fits in all. For each of these fits, the center channel is held fixed, and the peak height, sigma, and background coefficients are allowed to vary to get the minimum chi-square. The plot on this plot shows the chi-square of the 2048 fits as a function of the fixed center channel. This chi-square of the fits is usually very large and off-scale in regions where there aren't any peaks, unless the central channel is near a peak, in which the chi-square starts to drop. As you can see, the positions of the peaks are discernible as the minima in these chi-square, and candidate peaks are selected this way. Of course, the mu's and the sigmas of the valid peaks must also lie on the transfer curve for that detector. After finding all of the peaks, the list of mu's and sigmas is used to update the coefficients of the photon transfer curve. The most challenging software task is to match the found peaks with known gamma lines. The peak identification relies heavily on the channel versus energy function, which relates gamma energy to peak channel number. To the eye, this function looks linear, but it's actually a quadratic, as you can see in this plot where I've subtracted the linear terms from the data and the fit. We start with the list of lines found in the previous spectrum, and using their known lifetime estimates, estimate the expected intensities of these lines in the current spectrum. Using the channel versus energy function from the previous spectrum, we estimate the energies of the peaks found in the current spectrum, then try to match the new peaks with those found previously. Any peaks not matched to lines in the previous spectrum are matched to lines from a table of known lines. The identified peaks are used to update the channel versus energy function and the table of line intensities. This procedure successfully solves 99.97% of the spectra in near real time, and it catches most failures either through having a bad chi-square or C coefficients that are way out of bounds, and it will stop, in this case, pending intervention by a human using a special GUI that allows hand matching of the lines. Since the analysis of the current spectrum depends on the results of the previous spectrum, this GUI was used to start the process on day 1. Once the energy scale has been solved, we can zoom in on the region around the zirconia line. Because of the close proximity of the manganese line, we fit the region between 800 and 1100 kilovolts with a double Gaussian plus polynomial background. The fit parameters are the peak heights, the means, the sigmas, and the coefficients of the polynomial background. If one or both peaks are absent, the means and the sigmas of the absent peaks are fixed to the values predicted by the photon transfer curve and the channel versus energy function, and only the peak heights are adjusted. Of course, the quantity of interest is the resulting area of the zirconia peak, square root of 2 pi times the peak height times the sigma. The areas are plotted versus time to form a decay curve shown here plotted on a log scale. The residual activity from the previous shot is seen to decay exponentially, reaching a value of A residue at the time of the shot. At shot time, the activity jumps to a new level, then continues to decay with the same decay constant. Before the shot, the functional form of the decay curve is given by this expression, and after the shot, it is given by this expression. The values of A residue and A shot are determined by a two-parameter linear least squares fit to the piecewise decay curve, where we hold the decay constant fixed at the known value for zirconia. The value of A shot is proportional to the yield along this line of sight, and the proportionality constant, which we call the transport coefficient, is different for each RT-NAD detector because of the different amounts of materials in the way, like the port covers, the gunite, the chamber wall, and other structural elements. The transport coefficients for each detector are measured by firing special indirect drive exploding pusher shots. The indirect drive exploding pusher is a thin-shelled glass sphere filled with high-pressure DT gas driven by X-rays from a hull room. This gives us a uniform neutron emission with low hotspot velocity, low areal density, but at the expense of a relatively low yield. The yield of this shot is measured by a separate zirconia puck called the well NAD because it is situated in a reentrant well that gives it an unobstructed view of the implosion, while the individual RT NADs measure the activities along each line of sight. Since the yield is assumed to be isotropic, the transport coefficients for each detector are given by the well NAD yield over the individual RT NAD measured activity. Of course, both quantities are corrected for any hotspot velocity measured by the neutron time of flight spectrometers. To get an idea of the accuracy achieved by the RT NADs, we plot the ratio of the transport coefficients measured for two different identically configured shots for each detector. The RMS deviation of these 2 points is close to half percent, consistent with the expected errors in the measurements. Averaging these shots drives the errors down even further, so we conclude that the transport coefficients are determined to better than 0.5%. We can now use the measured transport coefficients to convert the activities of high-yield DT shots into line-of-sight yields. The circles show the measured RT-NAD yields. The colors refer to the color scale on the bottom, which ranges from plus or minus 10% of the average yield, which in this case is about 1.46 times 10 to the 16. The average fractional uncertainty in these points, which includes the uncertainty in the measured activities and the uncertainty in the transport coefficients, is about 0.46%. The color background is a fit of the data points to the sum of the real spherical harmonics up to L equals 2, plotted on the same color scale. The white spot over here indicates that the fit evaluates to a value less than 90% of the average yield. This shot had a rather large velocity of 110 kilometers per second in this direction. When we correct the RT-NAD zirconia data for the velocity effect, we get this distribution. Although the velocity correction removes a large L equals 1 component from the distribution, we still see regions of high yield which indicate that the areal density is low in this area of the capsule, and regions of low yield which indicate areas of high areal density in the capsule. And given that we have 48 RT-NAD data points having high statistical precision, we can extend the spherical harmonic expansion to L equals 4, revealing a little more detail in the angular distribution. Other shots show different morphologies in the RT-NAD data. Here are examples of velocity-corrected RT-NAD neutron yield distributions observed in different ICF shots. On the left here are examples of shots having what we call polar ice caps. That's buildups of areal density in the north or the south poles. We also see horizontally aligned neutron distributions, and occasionally there are even shots that show isotropic neutron angular distributions. You may have noticed in the first example that the velocity was directed along the direction of maximum yield, that is, minimum areal density. This is generally true for most shots, as you can see from these shots here, where the velocities are marked as directions are marked as with the X, and they are almost always in the direction of the highest yields or lowest areal densities. Now I will discuss some future work with the RT-NADs. First is the determination of fuel area density, areal density distribution from the RT-NAD data. Now the ratios of the RT-NAD yields are related to the difference in the areal density under the respective RT-NAD detectors. In the case of a point source, you can write down the formula for the difference here. And of course, this is only the difference in areal density. To get the total area density, you need to invoke some other formulations like the relationship between the downscattered neutrons measured by the spectrometers and the total area density. Of course, it's more complicated than this, and efforts to develop analytic formulations that are much more sophisticated are underway. Of course, my favorite involves postulating an areal density distribution as shown here, then using a Monte Carlo to predict the expected values of the measurements of yield and DSR given that areal density distribution. You then fiddle with this distribution in a sophisticated way and until you get predicted distributions that match the measurements. Another area of future work is to use the RT-NADs to measure hotspot velocity. The N-alpha reaction on aluminum produces a prominent line at 1369 kilovolts that you can see in the spectra on slide 7. The cross-section for this reaction cuts off at low energies, which is good, but it also has a different shape than the zirconia cross-section, shown here. So the ratio of activations of these two reactions is sensitive to the shift in the 14 MeV line energy. So this can be used to infer hotspot velocity. The NN prime reactions are also small below 1 MeV, and they're also small above 12 MeV, making them insensitive to low energy neutrons and the DT neutrons. But they are particularly sensitive to the 2.5 MeV neutrons from DD fusion reactions. The bromine in the crystal provides such a reaction that results in a 207 kilovolt gamma ray with a short 4.9 second half-life. The lifetime is so short that it only shows up in a single 10-minute spectra that overlaps with the shot time as shown here in this sequence of 3 spectra taken before, during, and after a shot. There is the line right here, which is proportional to the number of DD neutrons produced in the shot. The short lifetime, though, and the high dead time during the brief lifetime of this shot complicates this analysis, and that's what we're working on. And now back to my summary. NIF has the RT-NAD array to measure the neutron angular distributions. I've shown you how the detectors and software modules monitor the 909 kilovolt zirconia line and how the neutron angular distributions are measured with high statistical precision. Future work includes improvements in automation, determination of aerial fuel densities from RTNAD data, measurements of hotspot velocity, and analysis of the signal from DD neutrons. I also wonder what other interesting phenomena may exist in the RTNAD's 2 MeV spectral regime. Thank you for your interest.